Hello, Dr. Ko. In this video, I will be doing homework 4, energy balance. Um, in this problem, we have water from a 3 meter tall by 30 meter diameter holding tank uh, flows vertically down a 7 meter length of 1 meter diameter pipe into the bottom of a massive gold plated jacuzzi through a 10-inch diameter horizontal nozzle. And the water depth is kept at 1 meter by pumping water back into the tank so that it doesn't overflow. Some energy conscious king wants to know how much power the pump requires and the 100% efficient pump. If the pump is perfectly insulated and transfers no heat to the water, the question is a chiller necessary to keep the water at the same temperature? And so we'll start this problem off by drawing a picture of the scenario. So here we have our reservoir, and then we have water flowing to the jacuzzi right here, and then here is our jacuzzi, and this is, let me fix this. Here's our reservoir, and then from here the water goes back into the reservoir from the jacuzzi. Here's the water, this is the flow, the path, the approximate path that it takes. And from the problem statement, here are some dimensions. This is 1 meter. This right here is 3 meters. From here to here, 6 meters. And then here we can call from here 0 meters. We'll start right here. Then going down from here to here 3 meters, from here to here 6 meters, from here to here 1 meter. That will be, we can call this -10 meters since we're starting right here. Okay, and so before starting the problem, we're going to make a few assumptions, and that's going to be that the fluid flow here is going to be steady state, where the rate of the fluid flow into the jacuzzi will be equal to the rate of flow out of the jacuzzi into the reservoir, and this simplifies the problem a good amount. And so we're trying to first find the mass flow rate of the water entering the jacuzzi, and so we can use Bernoulli's energy balance equation. Bernoulli's energy balance equation is the change in pressure over the density plus gravitational acceleration times the change in height plus the velocity of the water at two different points, point 1, point 2, squared over 2, and that will equal to the non-flow work over the mass plus the frictional heating factor. This is Bernoulli's equation, but a few things to mention is that this right here is the pressure, this is potential energy. We're doing an energy balance, so this is our kinetic energy, this is our work, non-flow work over the mass, and then this right here is the frictional heating factor, but that should be 0 in this problem because it was stated in the problem that, where did we go? It was stated that the pump is perfectly insulated and transfers no heat to the water, and so there is no transfer of heat, there is no frictional heating factor due to the perfect insulation. Okay, and to go from here, we'll start simplifying the equation. Change in pressure will be at points 1 and 2, the velocity at points 1 and 2. So we need to define which points 1 and 2 we are exactly referring to. So since we're trying to find the mass flow rate, of the water entering the jacuzzi, we'll call the top right here 0.1 and the bottom right here 0.2. Okay. 1 second. Yep. That seems correct. Okay, and so from here we'll have the pressure at 0.2 minus the pressure at 0.1 over the density plus the gravitational acceleration times the change in heights, 0.1 and 0.2. And these change in heights are relative to where we marked as 0, right here. That's where we defined we're starting at 0 meters. And plus v2 squared minus v1 squared, the velocity at those 2 points, the difference squared over 2, and that is equal to the non-flow work over the mass. And we already mentioned that there is no frictional heating due to the perfect insulation. However, here we will have no work. This is all 0. There will be no work being done. The water is just flowing from gravity from point 1 to point 2. Something else we can simplify is that P1 is right here. This is point 1. It's open to the atmosphere, and so P1 will be 0. One more thing is that Z1 right here will be 0, just because we defined 0 meters right here at point 1. And so since Z1 is 0, since Z1 is 0, the velocity at point 1 will also be 0. And so from here we can simplify the equation P2 over rho plus G times Z2 plus V2 squared over 2, and that all equals 0. This is getting into a pretty simplified equation. So now we need to find, we don't know what P2 is, but we do know that the pressure is rho GH, and we can put that into our equation, rho GH, and that H will be the height at 2, and that's simply 1 meter right here. 1 meter is from here to here, the height of the water. And so we'll call that H2 over rho. So our rho's cancel, the densities cancel, plus G times Z2 plus V2 squared over 2 equals 0. So now our equation is getting even simpler. We can put in the values that we know for H2 and Z2. We know that H2 equals 1 meter, because that is the height of the water that we're looking at from here to here. And then Z2 will be from here, where we defined as 0 meters, 2.2, which is going to be negative 10 meters, since we're going down and we defined here 0 meters. So Z2 equals negative 10 meters. So from here, G times 1 meter plus G times negative 10 meters plus V2 squared over 2 equals 0. And so from here, we'll obviously have negative 9G plus V2 squared over 2 equals 0. And from here, we can solve for the velocity at 2. V2 will be V2 squared equals 18G by multiplying the 2 and adding the 18G over. And so the velocity will be the square root of 18G meters per second. And so now that we got the velocity, we can easily get the volumetric flow rate, because we know that the volumetric flow rate at 2, since we have the velocity 2, will be V2 times the area of the flow. And we can get the area of the flow since we're given the diameter of our pipe. The diameter of the pipe is 10 inches, and so the radius will be half of that, 5 inches. And since we want to stay with the same units, we can convert this into meters. So a conversion will lead to 0.127 meters. That is our radius. And so remember that we found here velocity 2. Now we're trying to find the volumetric flow rate at 2, which is V2 times A2. And the reason we're trying to find the volumetric flow rate is so that later we can find the mass flow rate. We'll be able to find our mass flow rate. Okay, and so our volumetric flow rate will be Q2 equals V2 times pi r squared. So Q2 equals, what is V2? Square root of 18g, you already found that, times pi 0.127, which is our radius, squared. So from here, we found out the volumetric flow rate at 2. So now we can figure out where the water leaving our jacuzzi. So since the problem statement says that the energy conscious king wants to know how much power the efficient pump requires, we'll be energy conscious and choose 2 different points in order to get our work, mass flow rate, and to solve the rest of the problem. These 2 points will be, let me use this, points 3 and 4, we can call them since we already used 1 and 2. Point 3 and point 4. Okay. And so, from here, what we can do, points 3 and points 4, makes sense. And since, entering and exiting points, point 3 and 4, and this will make sense once we apply Bernoulli's equation, do another energy balance. And so we can use the exact same equation, changing P over rho, plus G delta Z, plus V, and in this case it will be V4 squared minus V3 squared over 2, equals the non-flow work over the mass plus the frictional heating factor. This is the same in this case. We have the same system with the perfectly insulated pipes. This will be 0. But in this case, the change in P will be P4 minus P3. But if we take a look at these 2 points, P3, points 3 and points 4, they're both exposed to the atmosphere, and so the pressures will cancel out. So this entire term will cancel out. One more thing to note is that the velocity will not change from point 3 to point 4, and so this entire term will cancel out as well. And in this case, we actually do have work because the pump will be, there will be work done because we're using the pump. And so from here we can write G times Z4 minus Z3, and that all equals the work over the mass. And we can solve for the work. That will be G times M, the mass, times Z4 minus Z3. And this is not just the mass, this is the mass flow rate. Note in all of these, this is actually the mass flow rate, even in the beginning right here. And this right here is also where we found the volumetric flow rate. This is the volumetric flow rate. We define it with the dot, because rho equals m dot over v dot, or m over v. In this case, we're using the flow rates, the mass and the volumetric flow rates. And so from here, we know that at Z4 and Z3. 4 is right here, that will be 0 meters, and 3 will be right here. 3 plus 6, that's going to be -9 meters. And so we will have the work equals G times the mass flow rate times 0 minus -9, so we'll have a positive. So our work will be mass flow rate times G times 9. Okay, so now we got this expression over here, and the reason why we found this volumetric flow rate from earlier is because we will need it to get our mass flow rate right here. And since I said earlier that the density is the mass over the volume, or the mass flow rate, or the volumetric flow rate, we can get our mass flow rate by simply multiplying the density of the water times the volumetric flow rate. Okay, and so we can do the mass flow rate will be the density of the water times the volumetric flow rate, and we found the volumetric flow rate from earlier, square root of 18G times 8. Sorry about that, I was interrupted by a call. But like I said earlier, the mass flow rate is the density of the water times the volumetric flow rate, and we already found the volumetric flow rate from earlier, which is the square root of 18G times pi r squared, the area pi 0.127 squared. Okay, so now that we've got the mass flow rate, we can write our expression for the power, and that'll come straight from here. Sorry. From here. Okay. So we have rho square root of 18G. That is our right here. Since we found square root of 18G as our velocity, that is in meters per second, and this is kilograms per meters cubed, since it is the density of the water, we will assume we'll use 1000. Pi times 0.127 squared. This will be the area, so that'll be meters squared. All that's left is times 9 times G. G is meters per second squared, gravitational acceleration. All these units are important. And so the units combined, we will have, one second, yes, meters per second squared. So we will have seconds cubed times kilogram times meter squared, our final units for the power. The seconds add up to the seconds cubed. The meters cancel out for the meter squared, and we get kilogram stays the same. Those are the units. And so the power, after calculating, we get around 60,000 kilograms meters squared per second cubed. And we can use these units as joules over seconds. This is also watts. So the power is 60,000 watts, or we can just call them kilowatts, 60 kilowatts. This right here is the power required for the pump to pump the water into the jacuzzi. And since we're putting power into the system, we need to take power out, and so the system will heat up. We will need the chiller to counter that increase in temperature, because the problem statement stated is a chiller necessary to keep the water at the same temperature, and since we're putting power in, the system will heat up, And to counter that increase in temperature, to keep the water at the same temperature, we will need a chiller. So chiller is necessary. And that is the end of the video. Here is the work. Thank you.